All right, guys, so we're going to do fluid flow. So we're going to continue fluids. These next few slides, there might be more than a few, I don't know. But they're just going to be on so still fluids. So we're talking pressure, density, mass, volume, area, that kind of thing. But specifically now the fluids are going to be flowing. And they're going to be flowing laminarly, smoothly is what I'm trying to, is a fancy word for smooth. So not turbulent, but so we're going to start with something we call flow rate. And that's just a generic capital R. It just represents a number, specifically the amount of volume per time of the fluid. So it's the mass, like it says, the mass that flows in is equal to the mass that flows out, is what we call the continuity equation. So the idea is that you got this flow rate through the pipe, through one section of pipe, which is how much volume per time is coming through that pipe. And then what happens is when it connects to another pipe, because we have to have what goes in comes out, then the fluid flow in has to equal the fluid flow out. So what happens, we can take volume, and we'll just use, and this will work for any volume, but we'll use a cube just to keep it simple. Length times width times height. Well, if you take the length and the width, you get the area. And then that leaves height divided by time. Again, this works with all volumes. And you end up with an area of that shape times the velocity of the fluid. And then that's what, I don't know if that's hidden for you, but there it is. The fluid flow in is going to be equal to the area of the first pipe times the velocity of the fluid in that first pipe. And it's going to equal the area of the second pipe times its velocity. So typically, and I'll use the hose as an example. If you've ever had water coming out of a hose and you put your thumb over the end of it, or a water fountain for that matter, but you put your thumb over the end of it, you can narrow the stream of water and increase the velocity. So the area and velocity of the water coming into the pipe, that stays the same. But what you do is you decrease the area on the other side. So A1, B1, the one side of the pipe is going to stay constant. We're going to drop the area. We're going to squeeze the tube on the other side, which is going to decrease the area. But to decrease the area, the fluid is going to increase its velocity to keep everything equal. And then that's what we mean by the continuity equation. There's a challenge slide. We'll find out how we do that when we do that one. But I'm going to keep going with the notes here. Bernoulli's principle. So Bernoulli's principle's relatively straightforward. If the velocity of a fluid increases, the pressure decreases, and vice versa. So I'm going to go to the picture here. Put on the laser. Turn on pen. Pen or laser? Hold on. Laser pointer. Here we go. All right. So here we have a wider area of pipe. Here we have a narrow area of pipe. So, but going back to the continuity equation, this is a big area versus a small area, and these pipes are connected. So the velocity is going to be faster in area 2 than it is in 1. Because the velocity is faster, higher speed means lower pressure. The molecules are actually moving faster in this narrow section of pipe. We call these pipes Venturi tubes. Sometimes you see them in chemistry and stuff, or used as a vacuum. You can hook it up to a water faucet and create a vacuum. It can pull air out instead of pulling a fluid. But so the idea is you got, smaller area, so you got a faster velocity. Faster velocity means now we're in Bernoulli's equation, Bernoulli's principle, but the pressure drops. So if there is a low pressure on the P2 side and a higher pressure on the P1 side, the fluid in this pipe is actually going to get pushed up. And if it's strong enough, it can actually push this fluid all the way up into here and then shoot out. Velocity, that's Bernoulli's principle. And then if the velocity, I already said that. Oh, so some of the demo here, these are just demo slides. Sorry, I'm going to describe the demos, and then if you have the ability to do these, or hopefully you can try these. But actually, 2 of these you can try. The spinning whirly tubes, you'd have to have these silly toys. They're plastic tubes, and you spin them, and when you spin them, they make a high pitch. But what happens is the top, where you're spinning the top, goes really fast compared to the bottom. Where the pipe is moving really fast, you create a low pressure. And so the high pressure air comes up from the bottom of the tube and out the top, and then you hear that's the music tube. Spinning whirly tube. Oh, you can if you spin it fast enough, you can actually suck up. If you take like little paper hole punches, like little torn up pieces of paper, you can actually suck up. If you spin a tube fast enough, you can actually pull out the. You can use it as a suction, like a vacuum almost. This one you can definitely do. If you turn your faucet on, and then just take a spoon and hold up the back side of the spoon, the curved part of the spoon, right up to the stream. And what happens is the water will go over the back side of the spoon, and it'll create a low pressure. And the high pressure on the curved side of the spoon the air will push it into the faucet, into the water stream. And then floating, I think this is the one most people are familiar with, Bernoulli's. I have another one too. I'm surprised I didn't write this one down. So here, the ones that's on here, floating ping pong ball. If you take a hair dryer, or if you have a leaf blower and like a light beach ball, like when you blow up with air, um, you can point the leaf blower or hair dryer straight up, and then you put the ball in that stream of air. What happens is you've got fast moving air all around the ball, which creates a low pressure around the ball, and then the atmosphere comes in and holds the ball up. You can also do it if you have an HVAC, like forced air system in your house, not radiator, not convection flow, but forced airflow, where you have the vents in the floor. Get a balloon and just set it on that vent. Wait till the air or the heat kicks on, and um, what do I want to say, push, like that air is going to push the balloon up in the air, but then it's going to go around the balloon. So you're going to have this fast moving air around the balloon, and it'll just hover like a foot or two off the ground. And then the one I got, oh, here it's so here the other demo I was going to talk about. So this is um, so Bernoulli's principle leads to Bernoulli's equation, and it's just an energy equation. It's conservation of energy. So pressure is equal to force over area. That's related to work. 1/2 rho v squared. Well, that's a moving fluid. That's kinetic energy. And y is equal to a height or gravitational energy. So it's the gravitational energy in a fluid, the kinetic energy of a fluid, and the work of a fluid. So you don't necessarily have all three of these. This is just most likely what you would have. So on one side of the pipe, you'd have an initial pressure, an initial speed, and initial height. And that will be equal to a different area, um, a different connection of the pipe, either where it narrows, maybe it elevates into the second floor, stuff like that. But then it's the same equation. You got another pressure in that side of the pipe, velocity, and then a height change. This equation looks daunting, but if you just let the problem kind of set it up for you, if the pressure is equal on both sides, like it's open to the atmosphere. If you have an open container with a hole in it, both sides of that, the open container at the top and the hole at the bottom, would have equal pressure. They'd have equal atmospheric pressure. The P1 and P2 cancel out. Now there'd be a change in height, so you'd have gravitational energy difference, but one of those you could set as zero. If you set the hole as zero, then the y2 goes away, and then you can calculate the velocity coming out. Now, what's the velocity at the top? Um, well, if it's dropping, they would have to give you some indicator of how fast it's dropping or how fast it's moving. If what typically could happen is it's either so slow that it's negligible and we just make it zero, or they're refilling the container so it stays the same, and then this v is also zero. So a lot of this stuff can go away. It just depends on the problem. And then the rising paper demo. Just if you take a sheet of paper and you put it right under your mouth and blow across the top of it, you would think blowing across the top of it would blow the paper down. But what it does is it creates a low pressure on top of the paper, and the high pressure atmosphere underneath the paper actually pushes the paper up. It's a cool one to try. The gopher thing is just nature. Animals are surprisingly clever. So what happens is the gopher digs out a hole, and then one end actually gets mounded up, and then the other end they keep a little lower. So as the air goes around the mounded end, there's this, I forget what it's called, Kanadoa effect, I believe, where the air molecules kind of stick together and they go a little faster. The short of it is the air goes a little faster over the mound. Uh, Faster moving air, and this is the part we're going to focus on, faster moving air creates a low pressure. So the high pressure over here actually gets pushed in through the hole and out the top. And then the gopher actually makes like circulated air conditioned air. Not cool. I mean, it's atmosphere temperature, but it's still like a fan blowing on you. And then another example of Bernoulli's equation. Sorry. I just want to show you. So, well, let me go through it and then you'll see what happens. But Bernoulli's equation breaks down. So when we did fluids at rest, we had this equation. The P, well, I'm going to jump to it. P equals P naught plus rho GH. And then we made H positive. And so I didn't really address it at the time, and I don't know if you were thinking about it. Why is H positive? Why are we going down beneath the surface and making H positive? So it comes out of Bernoulli's principle. And I'm going to walk you through this. So P1, I'm going to set as the absolute. So we're underwater. This is P1 is the absolute pressure underwater. We're going to say the fluid's not moving, right? It's fluids at rest. So the V's are 0 on both sides. So there is no fluid kinetic energy. PGY1 is us underwater. So we're going to take that, make it a negative Y1. And then we're going to make the surface 0. That's where we get the positive H. So when we solve for absolute pressure, we add this negative gravitational fluid energy to the other side, we get a positive for the depth. That is the only reason. It's just the way we set up Bernoulli's equation. But Bernoulli's equation breaks down to fluids at rest. So it works for everything. And then we're going to do some class kick slides. I'm going to talk about... So we'll come back to problems later. But here, curveballs. This is interesting. So when they were... This also deals with the third law, Newton's third law. But it's called the Magnus effect. And Magnus noticed it when he was shooting cannonballs, and he saw that they were curving when they shot. So discuss pressure change. So for the third law, so here's what's happening: the air in this. So this object, this, I don't know what it is, cylinder is spinning down. It's pushing the air down. So guess which way? And it'll pause it here. There's the arrow. Right, that blue arrow. So that's the direction. The blue arrow is which way it's pushing the air. Right, it's pushing the air down. So which way does the cylinder get pushed? Is up. And then that's what happens with spinning objects. When you don't spin it, you create air just smoothly. Air goes around it relatively smoothly and has a wake, has some drag. When you spin it, so in this case now we're spinning again. It's pushing the air down. If you push the air down. The air is going to push the ball up. And then here's the part we'll talk about. The rolling tube demo. If you take a piece of paper and roll it into a tube, and then roll it off like an incline, it'll curve back into the incline as it falls. How curveball. So it is Newton's third law. There's also a pressure change though. There is a pressure difference, but they're mainly the third law is what's pushing what's pushing it. But in the process of doing that, it creates a low pressure and a high pressure. But when the object is moving with the direction of airflow, you got faster moving air on top, which creates a low pressure. You got down here, it's flowing against the airflow. So the cylinder's going to the left of the screen, the air is flowing to the right. So that's the slower velocity. So you get a high pressure underneath. So high pressure to low pressure, you also get a little pressure change that pushes it up. So you get the third law acting. There's a video of, again, I can't show you because the videos will get flagged from Google. But if you look up Veritasium, Magnus effect. So if you go back here, this Magnus effect in Veritasium, it should pop up. He just talks about what I just talked about, but the video is pretty good. It kind of gives you different examples, some more examples. Fluid flow, that's review stuff. And that is the end, guys. All right.